Welcome to Lesson 5. So far we've explored all the theory behind searching and ranking. Now we're going to look at the actual blueprint of our system. Which tools did we choose for the job and what was our reasoning? Let's quickly recall our two-stage search process. First, retrieve. We need a fast way to find potential matches in a huge dynamic pool of data. We've explored methods like LSH, quantization and graphs. Second, re-rank. We need an intelligent way to sort that retrieved list for maximum relevance, and we've explored learning to rank methods for this. Now, let's see what we actually chose for PISTIS. To do that, we had one guiding principle. The single most important characteristic of the PISTIS data marketplace is that it's constantly changing. Datasets are frequently being added, updated, and deleted. So, our primary goal was to choose technologies that could handle this high rate of change gracefully, without requiring constant, expensive maintenance. This made our choice for the retrieval stage clear. We chose locality-sensitive hashing, or LSH. Why? Well, graph-based methods are like a complex Jenga tower. They're very fast, but removing one piece, like deleting a dataset, is risky and can cause the whole structure's performance to collapse. Quantization methods require an expensive training phase. When the data changes too much, you have to rebuild everything from scratch. LSH, on the other hand, is like Lego bricks. Adding or removing a single brick is simple and it doesn't affect the other bricks. This makes it perfect for dynamic environments like PISTIS. For the re-ranking stage, we faced a different and very classic challenge, the cold start problem. Modern learning to rank models work by learning from user behavior, clicks, downloads, and so on. But on a brand new platform like PISTIS, there is no historical user data to learn from. The analogy is like opening a brand new restaurant and trying to create a most popular dishes menu on your very first day. You have no customer feedback to guide you. To solve this, we used a technique called weak supervision. Here's how it works. First, we, the experts or teachers, create a simple set of rules based on our own domain knowledge. For example, a rule might be more complete datasets are better, or fresher data is more valuable. Then we use these simple rules to automatically generate pseudo-labels for all of our datasets. Finally, we train a powerful, complex student model, a machine learning model, to learn from these thousands of automatically generated examples. You might ask, why not just use the simple rules? The reason is that the student machine learning model learns a much more nuanced and powerful understanding of the rules. It can capture complex interactions that simple rules can't. For example, it can learn that provider reputation is especially important for datasets that are less fresh. This gives a robust and effective ranking model from day one, which can then be easily updated with real user feedback as it comes in. So, let's look at our system architecture. Our system is designed as a complementary service to an existing data catalog called Pivot. Pivot is great at searching metadata, like descriptions, and our engine adds the missing ability to search by content. Our system is composed of three main parts working together: distributed query service, which is the orchestrator, the LSH component, the local search expert, and the re-ranker, the final curator. The first component is the distributed query service. This is the central brain of the system. It acts as the project manager for every single search query. It receives the user's search request, it sends that request to the local LSH components in parallel, it gathers all their candidate lists, it checks the user's permissions, and finally it sends the clean, authorized list to the re-ranker. The second component is the LSH component. An instance of this component is deployed at each data factory, that is, right where the actual data resides. Its job is simple. to index the local datasets and keep that index up to date. When a request comes from the orchestrator, it quickly searches its local index and returns only the best local matches. It's just like a local librarian who knows their own section of the library perfectly. The third component is the re-ranker. This is the final stage of the pipeline. It takes the combined list of candidates from the orchestrator. It then uses our pre-trained student model to assign a precise relevance score to each and every item. Finally, it produces the final, accurately sorted list of results that is presented to the user. So, here is the complete workflow. The user sends a query by example. 2. The orchestrator broadcasts that query to all local engines. 3. The local LSH engines find potential matches in parallel. 4. The orchestrator aggregates all the results and checks permissions. 5. The re-ranker scores and sorts the final combined list. And 6. The user receives a single, highly relevant ranked list of datasets gathered from across the entire distributed network. As you can see, we made very specific design choices to meet the unique challenges of the PISTIS platform. We chose LSH for retrieval because of its resilience and low maintenance cost in a dynamic environment. We used weak supervision for re-ranking to solve the cold start problem and create a smart ranker without any initial user data. And our three-part architecture, the orchestrator, the LSH component, and the re-ranker, allows us to effectively query distributed area while always respecting security and data ownership. Thank you very much for your attention. As always, if you have any questions, please feel free to send us an email.